बिस्मिल्लाहिर्रहमानिर्रहीम। अस्सलाम वालेकुम स्टूडेंट्स। आज हम लेक्चर 19 का पार्ट बी हम स्टडी कर रहे हैं, जिसमें कि हमने लास्ट टाइम जो लेक्चर 19 था उसको हम उसके अंदर जो टॉपिक्स हम कवर कर रहे थे उसके कुछ टॉपिक्स रह गए थे जो कि मैं इस पार्ट में अब कंप्लीट करूँगा, जिसमें जो सबसे जो पहला पार्ट था जो कि हमने डीसी ऑफसेट पैरामीटर्स हैं वो हमने देख लिए थे, और आज हम उसके जो फ्रीक्वेंसी पैरामीटर्स हैं जिसमें कि उसकी जो ओपैम्प की जो बैंडविड्थ होती है, किस रेंज ऑफ फ्रीक्वेंसी के ऊपर ओपैम्प को आप यूज़ कर सकते हैं, और जो स्लीव रेट है जो कि उसका एक और फ्रीक्वेंसी पैरामीटर है जो कि इम्पोर्टेंट है ओपैम्प के लिए, कि उस स्लीव रेट बेसिकली ओपैम्प की जो फ्रीक्वेंसी के ऊपर एक लिमिट सेट कर देता है ये पैरामीटर, कि फॉर अ गिवन स्लीव रेट द ओपैम्प कैन नॉट बी ऑपरेटेड अबव अ सर्टेन वैल्यू। सो इसकी जो फ्रीक्वेंसी ऑपरेटिंग फ्रीक्वेंसी की जो लिमिटेशन है उसमें ये दो पैरामीटर्स हैं, बैंडविड्थ और स्लीव रेट, जो कि डिटरमिन करते हैं कि आप ओपैम्प को किस फ्रीक्वेंसी तक ऑपरेट कर सकते हैं। सो इट इज़ वेरी इम्पोर्टेंट इन सिग्नल एप्लीकेशंस, जहाँ पे आप ओपैम्प को डिफरेंट फ्रीक्वेंसीज के जो इनपुट सिग्नल्स हैं वो अप्लाई करते हैं, और किस रेंज ऑफ फ्रीक्वेंसी के ऊपर वो सिग्नल्स को के ऊपर फंक्शनैलिटीज़ परफॉर्म कर सकता है, किस रेंज ऑफ फ्रीक्वेंसी के ऊपर आप उसको एक पर्टिकुलर एप्लीकेशन में यूज़ कर सकते हैं। These parameters are important as far as the operating frequency of the op-amp is concerned. Then we will see the op-amp data sheet for 741 at the end. So these topics we have covered in part A, in which we see DC offset parameters, DC offset voltage, input offset voltage, input offset current, and input bias currents. Then we see the total output offset voltage due to these input offset parameters, and we see the output is in error, that for no input, that is with zero input, the output of the op-amp is not zero, rather there is some value that appears at the op-amp's output. Now let me see what is gain bandwidth and slew rate of the op-amp. So these topics we have already covered in the last class, and now we are at this point, op-amp specifications with frequency parameters. So we are going to define first of all the bandwidth of the amplifier. The op-amp is designed to be a high bandwidth amplifier. So manufacturer try to design an op-amp so that the op-amp have a very high bandwidth, and the ideal bandwidth of an op-amp is infinite. That is, it should amplify over a wide range of frequencies, that is from 0 Hz to infinity Hz. But practical op-amp has an upper cutoff frequency that we will see what is the maximum frequency that the op-amp can amplify, and beyond that the op-amp gain is zero, or it cannot amplify the input signal. So practical op-amp has some internal compensation capacitor that is used to make the operation of the op-amp stable. So the addition of this capacitance reduces the gain at high frequencies. That is, this capacitance does not allow high frequencies to pass. Secondly, because of this internal compensation capacitor that is introduced in the op-amp circuit intentionally, so because of the fact that this capacitance is dominant, and that is the value of this capacitance is pretty higher than the parasitic capacitances due to the other devices in the IC, that is due to the transistors. Reasonably large internal capacitance is incorporated in the IC, whose value is relatively higher than the junction capacitances of the transistors. So due to that, this capacitance becomes dominant, that is the cutoff frequency due to all other parasitic capacitances is way higher. Because higher the capacitance, lower would be the frequency, as you know. So the gain roll-off is constant over a wide range of frequencies, because of the fact that the dominant frequency and the other frequencies are very far apart, so that gain keep on decreasing at a constant rate. That is, the roll-off would be at a constant rate of minus 20 dB per decade or minus 6 dB per octave. So this is the frequency response of the of a certain operational amplifier, in which you can see that this is a plot of frequency versus the gain of the amplifier. That we have seen in chapter 9 as well, the frequency response, in which we plot the gain on the y-axis and frequency on the x-axis. And for an op-amp, the response is starting, the gain would be maximum at 0 Hertz, and this implies that an op-amp amplifies the DC signal, that is the signal with the zero frequency, equally well as it amplifies the frequencies which are higher than 0 Hertz. So the operational amplifier is essentially a DC amplifier. The DC amplifier is the amplifier which amplifies DC signals as well. And AC amplifier are the amplifiers which only amplify the AC, and they do not amplify DC signal. So because of the fact that there is no coupling capacitors used in an op-amp, that is, the signals are directly fed at the input of the bases of the transistors in a differential amplifier. Because of the reason that there are no coupling capacitors used, so the amplifier amplifies the signals which are of low frequencies or up to DC. Then due to the internal compensation capacitor we have introduced in an IC, the op-amp has a certain cutoff frequency, after which the gain start decreasing at a constant rate, and the other cutoff frequencies which are very far from the cutoff frequency determined by the internal compensation capacitor. So the overall response would be determined by this capacitance only. So this frequency is defined as the cutoff frequency of the operational amplifier, where the gain of the response is dropped to 70% of the maximum value. Then there is another parameter defined as the F1, which is defined as the unity gain frequency. That is the frequency at which gain of the amplifier is 1 or at 0 dBs. So this is called the unity gain frequency. Another parameter defined as B1. B1 is defined as the unity gain bandwidth of the amplifier. So what is the bandwidth? Bandwidth of the amplifier is the frequency range over which the gain of the amplifier is remains constant or within the 70% of the maximum value. So this FC is the bandwidth of the amplifier with a gain of AV, and B1 is the unity gain bandwidth. That is, it is the range of the frequency over which the response of the amplifier is at unity. So these are the important parameters we are defining from this graph. That is, this is the differential gain or open loop gain of the amplifier, and this amplifier amplifies the DC signal. That is, the gain of the amplifier is at maximum at 0 Hertz, and it stay as a constant value for us as you increase the frequency, but at a certain frequency, after this cutoff frequency, the gain start decreasing, and its value becomes equal to 1 at a certain frequency. That is defined as the unity gain frequency, where the gain of the amplifier becomes 1. And then we define the unity gain bandwidth and the and the cutoff frequency of the amplifier. So a few important quantities are defined on the plot. One of them is unity gain frequency, where the gain is reduced to unity. The frequency at this gain value is called the unity gain bandwidth B1. That is, for an amplifier with the gain of unity, will provide the gain of unity up till this frequency called the bandwidth of the amplifier. So the amplifier will provide this gain of unity value up till this frequency, which is the unity gain bandwidth of the amplifier. So another frequency which is called the cutoff frequency, at which the gain becomes 70% of the maximum value and is defined as FC. So for a response with a constant gain roll-off, in fact the gain bandwidth product remains constant and is equal to unity gain frequency as given below. So from this plot, this response, we can draw a conclusion that the gain bandwidth product remains constant, and this product would be equal to the unity gain frequency, and is defined by this relationship, that F1, which is the unity gain frequency, this F1, and that would be equal to differential gain into the cutoff frequency. So from here you can see that this product unity gain frequency, this product gain into the bandwidth. This is the bandwidth for a gain of this much, and this is also the bandwidth f1 for a gain of 1. That is unity gain bandwidth. So gain into bandwidth product is always remains constant and is equal to f1, where f1 is the unity gain frequency. So we can further clarify this from this graph, as you can see that if I reduce the gain from the maximum value to AV1, for example, AV1, then this gain would be remains constant up to this point, and let me call this as frequency f1 up till this gain of the amplifier will remain at a constant value. And if I further reduce the gain, then this value of the gain I will achieve up till this frequency, that is f2, so that this gain into this new bandwidth f1, the product of these two would be equal to product of these two quantities, so that as the gain is reduced, the frequency is increased, so that gain into bandwidth product of these two remains constant. So AV1 into f1, that would be equal to AV2 into f2. So if you reduce this gain value, then frequency will be increased, so that the product will remain constant. So for example, if this value is for example 100, and this one is let's say 50 hertz, and if I reduce the gain to let's say 10, then frequency would be increased to a value 500. So that if gain is reduced, the frequency is increased, so that the product remains constant. That is 50 into 100 is 5000, and 10 into 500 is also 5000. So gain bandwidth product remains constant. So let's see an example. Determine the cutoff frequency of an op-amp having specified values, that is unity gain bandwidth as 1 megahertz, and the differential gain of the amplifier is 200 volt per millivolt, that is equal to 200 into 10 power 3 volt. Okay, so we have to determine the cutoff frequency of the op-amp. We know that from the last relationship, as f1 is equal to gain into fc, f1 is given as b1, and that would be equal to gain. Gain is also given. Gain is 20 into 10 power 200 into 10 power 3, and we want to find out fc, so fc would be equal to f1 divided by avd. So FC would be F1 divided by AVD, but so by plugging the value of F1 as 1 megahertz, and AVD is 200 volt per millivolt, which is 200 into 10 to the power 3. So by simplifying this quantity, we will get 5 hertz as the cutoff frequency of the amplifier, whose unity gain frequency is 1 megahertz. Next, another important parameter of a differential amplifier or operational amplifier is the slew rate parameter. Slew means to rise up. So at what rate value of the output voltage of an op-amp will increase, that rate is determined the slew rate of the op-amp, and it is defined by this parameter, that how fast the output of an op-amp can increase or rise from one value to another value. That is, for example, it is at certain value of 0, and how fast it will increase per unit time. So faster the rise in the output, the better would be the response of the op-amp against frequency. So if the op-amp output rate is slower, then the slew rate would be low, and for this the slew rate would be higher. So as the rate of the change of the output increases, the value of slew rate would be increasing. So in this direction, slew rate is increasing. So this parameter reflecting the op-amp's ability to handle varying signals is the slew rate, and it is defined as slew rate is equal to maximum rate at which operational amplifier output can change in volts per microsecond. So volt per microsecond is the slew is defined as is called the slew rate, that is out voltage, rate of change of the voltage per unit time, V by T, or volt per microsecond, is called the slew rate. So slew rate is defined as the change in the output per unit change in the input, which is volt per microsecond, with time is in microsecond. So the slew rate provides a parameter specifying the maximum rate of change of the output voltage when driven by a large input signal. So if an op-amp is derived from an input of a large value, so for example, if you apply a step input of, for example, 5 volts, the input of the op-amp, then how fast the output will be, ideally it should provide an output of 5 volt of this kind, but practically the op-amp output would show us little delay in the response. For example, the output would go like this. The output will increase slightly at a slower rate and reaches at 5 volts after certain time. So if one tries to drive the output at a rate of voltage change greater than the slew rate, the output would not be able to change fast enough and would not vary above the full range expected, resulting in signal clipping or distortion. Now another example, that for an op-amp having a slew rate of 2 volt per microsecond. What is the maximum closed loop voltage gain that can be used when the input signal varies by 0.5 volt in 10 microseconds? So in this case जो OP-amp का स्लो रेट है वो हमें उसने बताया कि जो इस पर्टिकुलर OP-amp का जो स्लो रेट है वो है 2 वोल्ट पर माइक्रोसेकेंड और then he is asking to find out the maximum closed loop voltage gain that can be used with an input signal which varies at this rate, that is input is changing in the step of 0.5 volts in 10 microseconds. So this is the rate of change of the input, and this is the rate of change of the output, and what would be the gain of the maximum gain of the amplifier that we can have, so that for this rate of change of the input the output is changing at this rate, so that we are not producing any clipping in the output. So we know that output is defined with input and gain as output is going to gain into input, and we can divide both sides by delta t in this equation. So this is the rate of change of output, this is the rate of change of input. These two quantities are given, and we can find out the gain of the amplifier from this relationship as bringing this one into the left hand side, and this thing is the slew rate, that is the rate of change of the output, and this is given as 2 volt per microsecond, and the rate of change of input is 0.5 volt per 10 microsecond. So if we compute this value, then it would be 40. So closed loop gain would be 40. So any closed loop voltage gain of magnitude greater than 40 would drive the op-amp at a rate greater than slew rate. So the maximum closed loop gain is 40 for this slew rate if input is changing at this rate. So next is we can determine the maximum frequency of the input signal that can be applied if op-amp is specifying with a slew rate value. That is the slew rate value would limit the upper frequency, upper maximum frequency up till which this op-amp can be used. So what is the maximum signal frequency? The maximum frequency at which an op-amp may operate depend on the both bandwidth and slew rate parameter of the op-amp. So one of the limitation on the upper maximum frequency is due to the slew rate of the op-amp, and the second limitation is due to the bandwidth of the op-amp. So these two parameters limit the range or limit the frequency up till which the particular op-amp can be used. Now for a sinusoidal signal of general form, V naught is equal to K sin 2 pi ft, where K is the peak value of the output voltage, and this is the sinusoidal function. So to find out the maximum rate of change of the output, we can differentiate this equation with respect to time. Then dV out by dt would be equal to K into cos of 2 pi ft into 2 pi ft. So maximum value would be equal to, take the magnitude of the derivative, then it would be equal to K into 2 pi f. So 2 pi f k would be the maximum rate of change of the output voltage, and because the maximum value of the cos theta is 1. So to prevent distortion at the output, the rate of change must be less than the slew rate of the op-amp. So this rate of change of the output should be less than the slew rate. So from here we can see that 2 pi f is equal to omega. So omega k should be less than or equal to slew rate. So from which we can find out the maximum frequency from this expression as f is equal to slew rate. F should be less than or equal to slew rate divided by 2 pi k, or omega should be less than or equal to slew rate divided by k. So additionally, the maximum frequency f that is determined from this relationship is also limited by the unity gain bandwidth of the amplifier. Next is example 10.14, that for the signal and the circuit shown in this figure, determine the maximum frequency that may be used. So for this input signal and the a circuit which is an inverting amplifier, that for this input we will get some output. The gain of the amplifier is determined by these two resistors. The magnitude of the gain of this amplifier would be equal to Rf over R1, which is equal to 24. So the output would be equal to gain into input. Input is 0.02. So multiplied by 24, we will get 0.48 volts at the output. So this would be the peak value of the output, which is represented by k. So if we know the value of k, we can find the maximum operating frequency with the relationship defined in the previous slide as omega is less than or equal to slew rate divided by k, where slew rate is defined for this op-amp as 0.5 volt per microsecond. So from which we can find out the value of omega, that is equal to 0.5 volt per microsecond divided by 0.48, which is equal to 1.1 into 10 raised to power 6 radian per second, where the value of omega is specified here as 300 kilo radian per second, which is less than the value we have computed. This is the maximum frequency that we can apply this to this op-amp without having any distortion at the output. So this signal frequency is less than the maximum value determined, so no distortion will be resulted in the output of the op-amp. So that's it, students, for today. Next time we will do lecture number 20, in which we are now going to we will start integrators and differentiators, few more applications of the op-amp, in which op-amps are used to perform certain mathematical operations. Till then, Allah Hafiz. Thank you.